Here's a question for you. How many natural numbers are there? Put it this way. If I'm using a natural number to represent your position in line, how big could that be? 1, 10, 1,000? That's a pretty long lineup, but it could be. The answer is that there's an arbitrary number of natural numbers. We just don't know how big it could be. And what that tells us is that we ought to be able to design a well-formed self-referential data definition for natural numbers. And what that tells us is we ought to be able to design a lot of functions on natural numbers really easily. That's what we're going to do in this video. First, I need to tell you about a primitive function in Racket you might not have seen yet called add1. And let's see, 0 is 0. Add1 of 0 is 1. And add1 of 0 is 2, and so on. So add1 takes a natural number and adds 1 to it. And there's another function, sub1. If I take sub1 of 2, I get 1. If I take sub1 of 2, I get 0. In a funny kind of way, add1 is a little bit like cons. Cons takes a short list and gives you a list one longer. And sub1 is a little bit like rest. Rest takes a list that's at least one long and gives you a list that's one shorter. So think of add1 as building a natural number up to the next biggest natural number, and think of sub1 as taking a natural number down to the next smallest natural number. I'm in naturalstarter.racket, and what I have here is a self-referential data definition for natural. Previously, we took the type natural to be primitive. Now we're giving a definition for that type. And it says, look, a natural is 1 of 0. That's the base case for natural, right? That's the smallest natural. Or it's add1 of natural. So if you look at the examples, example n0 is 0, and natural 1 is add1 of n0, that's 1, and add1 of n1 is 2, and I think you can clearly see here I can get a natural number as big as I want this way. This well-formed self-referential data definition will let me build up to as big a natural number as I want. But I also have to be able to take a natural number back apart. And I already told you how that's going to work. Add1 makes it bigger. Sub1 is going to make it smaller. So now let's look at the template. Template rules used. It starts with a 1 of in 2 cases. So that got me the cond. The first case is atomic distinct 0. There is a predicate, 0 question mark, in BSL that tests whether a number is 0. So that got me the 0 question mark and the ... And then, as I said, there's kind of this funny compound, this funny cons-like thing, add1, that takes a natural and makes the next biggest natural. So I'm treating this as a compound. But it's a funny compound because there isn't first and rest. There's just rest. There's just sub1. So there's the self-reference, because once I strip the add1 off with sub1, I'm left with a natural. So that's the self-reference in this type comment. That's the self-reference rule. And the presence of that self-reference is why there's a natural recursion here in the template function. Now I've got a little bit of the template commented out here. Just ignore that for now. The part that's not commented out is what the template rules are telling us to produce. So now we've got the type comment, the well-formed self-referential type comment, and we've got a template. Let's design some functions that operate on naturals. Let's see, the first one is a function that consumes natural, and it produces the sum of the naturals up to and including n. Let's see. That's going to be a natural, because if you add up any number of naturals, you get a natural. Produce sum of natural 0n inclusive. Define, we'll call it sum, n, and the stub is 0. Let's see, check expect. This is a self-referential data definition, so our first check expect should be for the base case, which is 0. The sum of 0 to 0 is 0. We need one that's at least 2 long. In this case, 2 long means at least 2 in size, but let's just do sum of 1 for now. Well, let's see, if I add up 0 and 1, that's 1. Let's do 3 now. So let's see, if I add 0, 1, 2, and 3, that's that, which is 6. There's some good check expects. They fail, but they're well formed. Let's get this template, copy it down, and I'll take this part that isn't supposed to be there out. We'll rename the template, rename the natural recursion, and let's see, what am I supposed to do here? The base case result is 0. And what does sum do? Well, these I actually kind of put in the wrong order, didn't I? This really happens in the other order because we start with the big N and we go down. So this is really 3, 2, 1, 0. The natural recursion, in this particular case, the natural recursion is going to be, this is going to be the sum of plus 2, 1, and 0. That's going to be the natural recursion. So what do I have to do with the natural recursion in order to get the result I want? Oh, I see. I have to add, and then there's something missing from the template, which is actually n. I need n. I'm allowed to add it to the template. Remember, a template is a skeleton of what you have available. In this case, the template didn't show us that we have the entire n available, but we do have it available. Let's try it. All 3 tests pass. Okay, let's do the other one. What we need to do is design a function that consumes natural number n and produces a list of all the naturals of the form cons n minus 1, all the way down to empty, but doesn't include 0. Okay, let's do that. Consume natural, produce list of natural. I'm not going to do a data definition for list of natural because we're producing it, not consuming it, so I don't need the template for it. I think you could produce the data definition for list of natural if you wanted to do it right now. It's not necessarily needed for a simple list type that we're going to produce. So produce cons n minus 1 all the way down to empty, not including 0. Define, we'll call it toList, and it'll produce empty as its stub. Let's do some examples. Well, again, we'll start with the base case. Whoops, not toList of empty. It consumes natural. It produces empty. So let's see, toList of 0. It's not supposed to include the 0, the base case. So 0 is the base case, but we don't include it. We'll produce empty. Gee, that's kind of funny what's going on there. Let's do the next one just to be sure we have it clear in our mind. toList of 1. Well, let's see. We're never supposed to include 0 in the result, but there's nothing that says we're not supposed to include 1 in the result. So this looks to me like it should be cons 1 and empty. And that makes sense because the next number after 1 will be 0. That's going to produce empty. So it's cons 1 onto the result of the natural recursion, empty. That looks pretty good. The rule is we have to do one that's at least 2 long, though. So let's do that. toList of 2 is cons 2, cons 1, empty. That looks pretty good. Let's run them to be sure they're well formed. They fail, so they're well formed. We'll go up here and get the template again. Command E lets me see more space. I'll take out this part that the template's not supposed to have in it. I rename the template and the natural recursion. Let's see, the base case result is empty. And what's the result in the case of recursion? Well, I'm supposed to cons. This is always, that's the natural recursion in the case of 1. That's the result of the natural recursion in the case of 2. So I'm supposed to cons the current number itself onto the natural recursion. Run that and it works. Oops, I forgot to comment out the stub. Oop. All 6 tests pass. Now at this point, having done 2 of these, or maybe after I wait till I've done 10 of them, but if you do 10 of them, you'll see that it's always nice to have the actual natural number. So even though the template rules themselves didn't put it in the template, what I'm going to do now is go back to the template and put it in along with a note that says template rules don't put this in, but it seems to be used a lot, so we added it. The key thing that happened in this video is we had this insight that there's an arbitrary number of natural numbers. So that means a well-formed self-referential data definition should describe the natural numbers. So that produced a template with a natural recursion in it. And once we had that template for the natural recursion, these functions actually were super easy to write. So have some fun writing some more of these functions that operate on natural numbers. I think you'll find that they go pretty quickly because the template really gets you almost all the way there. Once you've practiced those, then go back to some of the harder stuff we did this week, especially having to do with the reference rule. The reference rule is the place so far where working systematically helps you the most because it really helps you break what would otherwise be complicated functions into 2 parts. So be sure you follow that reference rule.